model to data. Just starting out, are there any questions anyone's had pop up since maybe the first couple times we met, or the lectures online? Fantastic. So let's get into it. I'm sure you'll have plenty of questions. So this is lecture 7. We're fitting models to data. When I say models, what am I referring to? Like trains, robots. That's going to be mathematical equations, right? So we're fitting these models, these equations, back to data, right? We're going to see how we can. Here are the objectives we're going to cover them as we get to them. First thing we're going to talk about is simple linear regressions. You know what a simple linear regression is? We basically want to try to predict how change in one value can predict the change in another value, right? So we're going to look at this. This example we're going to talk about is going to be, was talked about in section 6 here. But basically, the goals here, we're trying to get, basically, we have a set of data points, right? We're comparing two values together. Say, for instance, we're looking at like blood pressure and LDL or something like that. Any two values here, we're going to be able to get sort of a data plot on a graph, and you're going to be able to try to get a best fit line to that. So we're going to see if there any kind of correlation between these two values that come up here, right? So this is what a linear regression is going to help us to do, right? Basically, it's trying to fit a simple model, or basically, and again, when we're talking about, best fit lines, you guys remember what the equation for a line is? Y equals mx plus b, right? So that's basically the simplest model we can come up with, and so that's what we're going to be referring to today. We'll get more into it a little bit later on, talking about multiple regression models and things like that. But this is kind of the simplest one we can come to, right? So basically, all we're trying to figure out is the slope and the intercept here, so that way we get our y equals mx plus b. Simple as that. Okay, so looking at, and again, I think in lecture 6, I believe this is one of the examples we use, but we're looking at two variables here, right? So we're looking at insulin sensitivity, and we're also looking at the fraction of fatty acids. So basically, they're looking at a particular type of fatty acid chain that was located within the cells. They're getting a percentage, right? So basically, the fatty acid length was between, say, 20 and 22 carbons here, but they're looking at the percentage of those fatty acids that were present within the cells, and then comparing that to insulin sensitivity. Okay, their hypothesis was that there's a relationship between having a higher percentage of these fatty acids present and having more insulin sensitivity. Okay, so we're looking at that and say, well, is there any sort of correlation between these two, right? Now, keep in mind, I'm not saying causation, because does correlation imply causation? No, we're going to find it's not the case. We can only find that out through actual experimentation. But basically, I'm going to show you the graph here in just a second. But we're going to find, and they proposed here with a simple model, that insulin sensitivity, which we're going to find on the y-axis here, is going to be a linear function of that percentage of those fatty acids, which is going to be on the x-axis, okay? And again, typically your x-axis is going to be your independent variable. You remember what independent variable meant? It's the thing that I'm setting, right? So again, I'm changing that value, or I'm organizing the data based on that value, whereas the insulin sensitivity is going to be the independent variable on the y-axis. I'm sorry, the dependent variable is what I should have said. Dependent. Dependent just means that it's going to be contingent on the change in my independent variable. Okay? So as I'm changing that percentage of C20 to 22 fatty acids, I'm going to see a change, a dependent change in the insulin sensitivity there. Okay? So anyway, so here we're going to find, as I mentioned, the insulin sensitivity is the y. X-axis is going to be that percentage of the fatty acids there. The intercept is b, and then my slope is m. If you go back to your high school math classes, I haven't looked at this stuff in a long time either. But again, just take it for granted here that this is the equation for a slope of a line. Anyway, so again, notice here that this does not account for random variation in the data. It really just looking at the relationship between these two particular variables here, right? And again, the standard assumption here is that we're pulling this data from a Gaussian distribution. When I say Gaussian distribution, what does that mean? Anyone remember? Normally distributed, right? It's just going to say that the variability there is not being unduly affected by any sort of outside circumstance. It's completely random, right? So again, it's just a random distribution. Again, we know that that's a big assumption to make. Right? If you go back and look at those tests for normality and things like that, you can find there's certainly a lot of non-Gaussian distributions out there, but our assumption here is just a Gaussian distribution, okay? And again, let's say otherwise, just assume that we're pulling from a normal distribution, normally distributed set of data here. Anyway, right, so our goals here are we're trying to find the values for the intercept and the slope. They're going to help us to most likely be correct and quantify some of the imprecision here with the CIs. When I say CI, what does that stand for? Right, it's our confidence interval, right? Because again, when I say that, hey, I'm trying to take a set of data and apply it back to a population, is that always going to be 100% correct when I do that? No, right? Because again, I'm taking a small sample set, I'm maybe only taking, say, 30 people, and trying to apply that back to a population of millions, like you're going to find there's some variability there. And that's what that confidence interval helps me to try to define. It's like, I'm pretty sure it's something like this value, but I'm going to say that I'm going to give myself a little bit of wiggle room there and say, well, 95% chance it's probably between these two values here. Anyway, so we're going to look at the CIs and see how those are going to be represented on the graph here in a second. And again, we're going to be thinking about this model graphically, and I'll show you some pictures in just a moment here. But again, our linear regression finds the best fit line. And I'm sure most of you probably played around with Excel and making, scatter plots and things like that. Has anyone ever tried to fit like a best fit line to their data? Maybe if you're like in an organic chemistry class or something. So you've probably done this before. We're going to look at what this values kind of mean for us in terms of the medical context, right? So anyway, looking at this, imagine we have our values of these fatty acids here on the x-axis. We have our insulin sensitivity on the y-axis. And so you can notice here that as you plot the data points, again, this is our independent variable. This is our dependent variable here. You're going to find there's sort of, if you just looked at it without the lines there, you could probably see a good relationship there. It looks like, it's heading in one direction in particular. And so basically what again, computers do this for us. They're going to put this best fit line here. And so the values around this are those confidence intervals, right? So that's kind of helping us to say like, well, we think the best fit line is here, but it could be more accurate. It could maybe be potentially something like this. Again, my lines are not very straight, but you kind of get the idea. Again, it's not very scientific that I'm doing this, but the actual line could be somewhere around that range, right? But again, this is the best fit line. This is what we think. This is kind of like our average line, our mean line that we're thinking about could actually fit into that. Boy, I need like actual tablet to draw some of this stuff because this looks really bad. And so you can find that they will report tables like this. And again, all this data is not necessarily necessary for our purposes, but some of the things you can look at would be, and again, this is going to be, the important thing here is the slope here, right? So the slope means what basically? Well, it means that if I have a value change of 1 in the x-axis, this means that I should have a value change in the y-axis of about 37. So if I go up from that percentage of those fatty acids, say from 1 to 2, I should see a change in my insulin sensitivity of about 37.21 milligrams per minute, whatever the value was, right? The units were there, right? That's what the slope is basically telling me, is like, what is that, that degree of change. If it was a larger number, if it's a larger slope, that means that it's a much more steep sort of curve you see there, or that line's much steeper. If it was a much lower slope, smaller slope, you'd find that that value would not be quite as steep. You see a smaller change as you change that dependent variable there, the independent variable there, right? We'll talk about R squared in just a few minutes here, but let's just focus on the slope here and look at these best fit lines. Yes, sir.
You said if I have a change in value of 1 in the x-axis, I should see a 37.20 change in the y.
That is true.
Okay.
Yeah, so again, if you were to look back at that picture there, the graph with the best fit line, you see that if you bumped up the value of x by 1, you should see roughly that 37 increase, right? And so that's basically what the slope is just telling us, is how big of a change you're seeing there. So the larger value means you're seeing larger changes by changing the value of x. Smaller slope means you're changing that value is going to have a much smaller difference as you change that independent variable there, right? So again, looking at the slope, and again, this is just kind of reiterating the points I've already talked about. The best fit line shows the slope is 37, which means I increase that percentage of C20 to 22 by 1, and the average insulin sensitivity should go up by 37.2. Now, would that apply to every single patient out there? No, but that's the average. That's what we think is, to apply to most patients. And again, that's why we have confidence intervals that are going to be around that, to show that there's going to be some variability there. So if I were to apply that back to whatever bigger population I wanted to, I could say that, okay, well, the confidence interval, the slope range is between 16.7 to 57.7 there, right? So again, it shows me that I'm confident, within a 95% chance that the actual value is going to be somewhere between these two values there, right? And again, how could I get that confidence interval more narrow? I can have a bigger sample size, right? So if I included more people from that population, I can get a bigger sample, and that would probably help to narrow up my confidence interval. That's one of the best things you can do to narrow confidence intervals, is to get more people involved, right? What do you call it when you have a bigger sample size? You have more, think Tim the Toolman Taylor, more power, right? Anyone, home improvement, no? Are you guys aged out beyond that too? Okay, yeah, thank you. Okay. Ancillary to that, Tim the Toolman Taylor did a lot of cocaine as well. So, there's that cultural touchstone. Anywho, point being is that you get more power the more people you have in your sample size, right? Because again, that gives you the ability to detect bigger differences there. So you can go back to those lectures. When you view that, you'll see that power is going to be a really important concept with that. Okay. Anyway, so looking at this, we know that the actual slope of that line could vary between, you know, say 16.7 to 57, but we're going to say that our average is probably going to be about 37.2, right? So again, you know, we're not going to be 100% confident in anything, but we can say with 95% certainty, there's probably somewhere between these two values. Now going over to the y-intercept, now if you notice here that when x equals 0, that your y-intercept would actually be negative here. Now again, when you're looking at these lines, you may find they start to veer into, if you kind of carry them out into infinity in either direction, you'll find they get to the point where they become not clinically relevant. Because can you have a negative insulin sensitivity? I guess it's maybe where you're spitting glucose out of your cells back into the bloodstream, like that. Maybe that would be negative insulin sensitivity, but that doesn't really happen there, right? So sometimes you'll find these values not to be, you know, biologically or physiologically relevant, but again, it's part of the equation there. Do you have a question?
Yeah, just to clarify, you said the bigger the sample size, the smaller the confidence interval.
Yes, because again, as you get closer and closer to that whole population size, you can be more certain that yes, you know, this is the actual population mean. Because again, I can never know what that whole population average is going to be, but again, I'm just trying to make a best educated guess here. Yep, for sure. And so again, it's not a scientifically relevant value when you're looking at something like the y-intercept being negative there. But again, it's a helpful when we're actually trying to figure out what our best fit line is going to be. It's part of that equation there. Okay. So anyway, looking at that best fit line, you know, as I mentioned, you're going to have the confidence intervals. Those are the shaded areas that were around there. Again, that shows us that the actual line could be somewhere within that shaded range. But if I had more individuals, if I had a larger sample size, I could probably end up getting something where the shaded areas would be more narrow, and I have a better idea what the actual best fit line would actually look like. Okay. And again, sometimes you're going to have values that fit outside of that. So for instance, in the case we were looking at that graph, you know, only 6 of the 13 points were within the confidence bands. That's okay. That's going to be totally fine because, you know, we know there are going to be things like outliers are going to fit outside of that line. This is just a 95% confidence interval. Some people are going to fit outside of that 5% there, okay, or within that 5%. So again, just an idea, this is a lot better example, straight lines here, but again, the actual line could be anywhere between the shaded areas here, as long as it's a straight line, because again, this is just a simple linear regression. We're not talking about any kind of funky curves or anything like that. It's just a straight line we're looking at here. Okay, so going back in, some of the other values we see here is we have an r-squared value. So basically, what this helps us to determine is how much of the variance in the insulin sensitivity we have is going to be accounted for by the linear regression model. Basically, what that means is that when you have an r-squared value, something like 0.59, that means that about 59% of the variability in the insulin sensitivity, which is again our dependent variable in this instance, is accounted for by that model. Okay, so that means about 59% of that variability is accounted for by the percentage of those fatty acids that's present. Now, what does that mean? Well, it means there's probably, say, something like, you know, 41% that's going to be dictated by something else, right? So there's lots of other factors that go into describing the insulin sensitivity. And so this is just showing us that this particular model doesn't describe everything. It doesn't take into account all variability, but it gives us some idea of what the variability is kind of accounted for by that our independent variable here, okay? And we start to get into multiple logistic regressions. We'll look at that a little bit later on. We're going to find that we can incorporate more variables into that to get a better idea of what is going to be causing a lot of this variability here. But just know when you see r-squared, it tells you how much variability is accounted for. Now, if I had a really good model where all the variability was being accounted for, my r-squared value should be what? It'd be 1 in that case, right? That means that there'd be a straight linear relationship between increasing that fatty acid percentage and the insulin sensitivity here. But we're going to find that in most cases, there's more variability. Again, people are complicated. There's going to be a lot more variability that goes into than just one factor here, one independent variable. So again, lower r-squared values would mean what in this case? Yeah, the model's probably not very good at representing the variability here. My independent variable is probably not very good at trying to estimate that insulin sensitivity. So if I had something like shoe size located on there, how much do you think shoe size has to do with insulin sensitivity? Probably not a whole lot. So I'd probably see my r-squared closer to 0, right? So there's no relationship, but there's no amount of that variability that's accounted for by the independent variable. You're going to find that it would be very close to 0, right? Maybe some relationship, but there's probably not very much, okay? That just goes to show us that. Now, a p-value in this case, again, what does the p-value tell us? So again, this is a very important point to go back to when you're reviewing the lectures online, but the p-value is telling us what are the chances that we would get these results just by random chance alone, okay? And again, the classic p-value you're looking for is what? Anyone know? 0.05, right? So if I had a p-value of 0.05, that means that there's a 5% chance that I would find results like this, or more extreme than this, just by chance alone. Okay, it's a pretty low chance, but it doesn't mean zero, right? In this case here, we have a p-value of 0.0021. That means that there's a 0.2% chance that the variability here is just due to random, that we would get a graph like this just by random chance. Does that mean zero? No, it's 0.2%. So it's pretty low probability that we'd actually get these values just by random chance alone. So it probably shows that yes, there is an actual relationship here. There probably is a correlation here that is not explained just by random chance alone. Okay. Now again, what would you get? And again, going back to, anyone remember what the null hypothesis is? The null hypothesis just means that there is no relationship here in this case. So again, you have to think about it on a case-by-case basis. Here, you would say that there's no relationship between insulin sensitivity and this percentage of fatty acids, right? So the null hypothesis would be that there is no best fit line. The line wouldn't make any sense with the data because there's no correlation here, right? What we're doing now, because this p-value is less than 0.05, we can say that yes, there is a correlation. We say there's very low probability this is just due to chance alone. So I can reject that null hypothesis and say that yes, there is a correlation here. That it looks like as I increase that percentage of fatty acids, I'm getting an increase in my insulin sensitivity. Okay. So based on that low p-value, yes, I think I can reject that null hypothesis and say it's very unlikely this would be just due to random chance alone. That makes sense? Okay. All right, so looking at this, again, correlation in this linear regression is going to be related here. When we're doing this, we see that the null would be that there'd be no correlation whatsoever between X and Y. So again, if I did something like shoe size and insulin sensitivity, I probably wouldn't find very much correlation there. I'd probably find a p-value that would be greater than 0.05 that would say that, hey, this is probably likely due just to random chance, right? And again, if you were to look at the null hypothesis for a linear regression, it would just be a horizontal line. Would be correct, right? It shows that there's no correlation between the two whatsoever. Typically, if I see a positive line, so a line heading up and to the right, that means there's a positive correlation there, whereas I increase one value, the other value should also increase, right? If I had a negative correlation, right, and like say an inverse correlation there, you'd find that as the value for X increased, the value for Y would decrease, right? So again, either one of those could be significant, right? Either one of those could be statistically significant and could have a p-value less than 0.05. If it's a straight line though, just straight horizontal line, that means there's no correlation between the two, and that's my null hypothesis that says that, hey, there's no difference between these, okay? And again, looking at this correlation in linear regression, the data set here is going to be identical, so the p-values would be identical here as well, right? So making these comparisons. So again, that 0.02 is still going to stand here. All right. So again, our assumptions when we're making linear regressions is that the model is correct. You know, obviously not all relationships are going to be linear, and sometimes you're going to find that we have to kind of fudge the numbers a little bit to try to make it more linear. So sometimes you'll take like the log of a value that oftentimes will take something that's more exponential in nature and make it more of a straight line. We'll look at some examples of that later on. And again, the linear regression is going to be defining a line that's going to extend kind of in both directions infinitely, but just know that at some point you're going to get outside of the range of kind of clinically relevant sort of values there. Like I mentioned, you can't have a negative insulin sensitivity, so it doesn't really make sense from a physiologic standpoint. And again, when you're looking at these linear regressions, you're using X as your independent variable that's going to try to predict the change in the dependent variable, which is on the Y-axis here, okay? So again, the change in those fatty acids, looking at how that affects the insulin sensitivity directly, okay? So anyway, as in this example, you see here that we're looking at that percentage change, seeing how that's going to be changing the insulin sensitivity as you go along. We obviously saw a positive correlation with that. Okay. Now again, other assumptions, we're going to see that the scatter of the data is going to be Gaussian. Again, you can do tests for that. You can do those normality tests. And again, my favorite joke is always to say that I failed every normality test I've ever taken. But you can see here that, again, you can test that. You can run those things. But most of the times the assumption is that, yes, this is randomly distributed. I'm pulling from a random data set. The yes, it should be a Gaussian distribution. Variability shouldn't really change along that scope there. So variability in the insulin sensitivity shouldn't change when you have very high values of X. And then these data points are going to be independent. When I say independent, what does that mean? It would mean that I'm not using like the same person twice, right? I couldn't use one person, say 6 months apart, to try to get different values. Again, that would be not an independent set of data there. We have different tests we can use for that. And so sometimes you'll have studies where you do like a pre and post, where you may take someone's blood pressure before an intervention, you take it afterwards, or maybe you try 2 different interventions before and after, and you're measuring the same person twice. That is going to be a paired data set, right? When you're looking at independent data sets, you're looking at people, completely different people. You're not using twins, you're not using anything like that, that's going to maybe have interactions with one another. And again, X and Y values shouldn't be intertwined. So for instance here, you wouldn't want to use something where, one directly affects the other one. So I guess for instance, trying to think of a good example of this, maybe like blood glucose and HbA1c, because again, we know those are automatically intertwined with one another. Probably wouldn't be a good example there. But again, looking at fatty acid percentages versus insulin sensitivity, we have no idea if those are really interacting with one another. That's what the data is there. That's what the experiment's for in those cases. Okay, and we should be able to measure X pretty precisely there. Again, that goes into the fact that we should always assume that our data measurements are being done correctly. However, you want to always verify those sorts of things, especially when you're the one doing the experiments. Okay. So looking at comparisons of linear regression and the idea of correlation. Correlation is just trying to quantify that degree that the two variables are related here, right? When the fact that it does not fit a line necessarily. And again, this is telling us the direction, the extent to which these two values are going to be changing, right? So as I have a change in X, what is my change in Y going to be? That correlation there. In these cases here, you don't really want to think about cause and effect. You're just looking for the relationship. You're not necessarily saying that one is causing the other in this cases here. You can't really determine that just based off correlation. In this case, you could also flip X and Y. It probably wouldn't actually matter which one is which, because you're not necessarily saying that one is causing the other. You're just looking at that relationship between the two. On the other hand, though, when you're doing just a regression, this is getting more involved here. This is where you're going to start to think about the cause and effect. So what you put as your x-axis, what you put as your independent variable matters very much, right? So if you think that the change in that fatty acid content has an effect on insulin sensitivity, you have to have the x being that fatty acid concentration. You can't interchange them at that point there, right? And this will be important when we're looking at some of the other values and some of the other type of regressions we'll see here in just a minute. Again, this is predicting X, or I'm sorry, trying to predict Y from whatever we set as our X here. Okay, so again, this has to be the dependent variable. This has to be the independent variable. Okay, some other things. Again, so we say linear, that just means that we are looking at one particular type of model here. This just means we're looking at one straight line as opposed to, say, logistic regression or something like that. And then when you see simple versus multiple linear regression, this is where we're kind of getting into looking at more than one independent variable. So we'll show you some examples of this in just a minute. A simple linear regression is when you only have one x variable. So again, the example we were looking at was a simple linear regression. If you were to have multiple x values, so for instance, if you were to say include, say, age as affecting insulin sensitivity, now you start to have a multiple linear regression. Now you can start to take into account multiple factors here and see which ones are playing a role in causing that variability. And we'll go more into detail on that in just a few moments. Okay. Models. Again, when we're forming these models here, the idea is to try to get these best fit values and try to get the best idea for that slope, or that equation for the line is going to be able to fit that data best to that model there. So we're going to use like a foot and a shoe sort of metaphor here in just a moment. But basically, the model is just a representation of something else. Typically, these models are fairly cheap to perform. They're fairly cheap to come up with. And again, we can use, once we have a model, say we take a data set, say I took the 60 of you or so, and I made looking at the relationship between, say, shoe size and heart rate or something like that, I could look at that, and then I could take that model and then try to apply that to other people, right? So I could try to apply that to a larger population and see how that actually holds up. And again, that can be a nice way to, and again, when you look at things like creatinine clearance, for instance, this is one I always go back to. Creatinine clearance was not done based off of, looking at thousands and thousands of patients. They did one study basically where they looked at, smaller subset of patients. They looked at their age and their weight and their creatinine, serum creatinine, all these different factors, and they made a model based off of that. And that's how we got the Cockcroft-Gault equation. So we have like the MDRD equation. These are different models that were designed based off of a study they did to try to fit that data that they had. Okay. And again, are they going to be perfect when you apply that out to the greater population? They're not perfect, but they're pretty good for the most part, again, depending on who your population is going to be there. Anyway, again, we're trying to fit these models back to the data that we have, and then we can extrapolate from there. Again, so when we're using regressions, we're fitting that model to the data. So we'll take a data set, just like we've been doing previously in this lecture here. We're taking that model, or taking the data and trying to fit a model to it. Basically, your data, if you consider those the feet, you consider the model to be the shoe you kind of form around it, right? So again, you need to find the best shoe that's going to be fitting there. If I have my normal size foot and I try to put a size 12 around it, it's just not going to fit. If I try to put a size 15 around it, it's just going to be too big. You need to find just the right size in there. And again, it's very hard for me to find shoes, so take pity on me. I'm just kidding. Anyway, you got to find just the right fit, right? So again, sometimes you're going to find multiple data or multiple models that are trying to fit it just right in order to get the best kind of fit there, right? So looking at comparing, we can see that comparing models is a big part of the statistics we're going to do as far as the medical literature goes. Again, you want to find out that you can't just use one parameter to try to predict things like insulin sensitivity or try to predict things like causes of mortality, etc. Oftentimes you want to incorporate multiple different variables in to try to get the best fit, right? So for instance, we were looking at that example before, that R squared value was only 0.59. That means only 59% of the variability was being explained by the change in that fatty acid content. Well, I want to figure out what else is causing all that variability, right? So by including more factors in, including more independent variables, I can start to get an idea of what those are going to be. And then I can start to control for other variables and try to make sure that I get rid of things like confounding. And what is confounding? Besides this class, very confounding, right? These are things that are going to be skewing your data, right? So we'll look at some examples of that a little bit later on. But for instance, looking at things like creatinine clearance, like, if I was just looking at the effect of, ACE inhibitors on preserving creatinine clearance, you'd have to take into account the fact that as people get older, they're going to have less creatinine clearance, right? Because the kidney function goes down with age. You have to include multiple independent variables here to try to get an idea of what all is going to be factoring in when we're looking at one particular dependent variable, whether it be creatinine clearance, whether it be insulin sensitivity, whether it be PFTs, whatever it happens to be that you're looking at as your outcome variable here, okay? So again, a model too few parameters won't fit the data very well. You won't get a very good R squared value, and one that has too many parameters you're going to find may fit the data too well, and then is actually going to be not very applicable to your greater population there, right? So for instance, when you're looking at, say you're comparing different creatinine clearance equations, if you look at Cockcroft-Gault, you'll look at and see that it only includes the patient's weight, includes the patient's age, and their serum creatinine, and then whether they're man or woman, right? Now, if you looked at something like the MDRD, does anyone remember what else they include with that? They also include race as well, because they actually took into account. They said, okay, well, if you're African American, then you had this different sort of equation here. We had this fudge factor versus if you were Caucasian, right? So again, those are some of the things you have to take into account. Is that, okay, well, how many variables are they putting into this? Sometimes that can make the data fit the model a little bit better when you try to extrapolate that out to the whole population. Okay, so just some things to consider. So again, when you're looking at linear regressions, when you're trying to compare models, you'll see here that typically the null hypothesis is just going to be a straight line, meaning there's no relationship, there's no correlation between x and y, okay? When you're looking at linear regression, though, we were trying to say that, okay, well, this is the best fit line to fit that data. And again, these data points are the same between the two. We say that, okay, we think this is a much better fit for that data there, and this is where we're going to get that p-value from, right? Because again, that null hypothesis means that there's no relationship. We want to try to reject that. That's what we're trying to find, okay? And again, to reject that, we need to have a p-value that's significant, which is usually less than 0.05, right? This is usually going to be our level for significance, as we'll see here. So anyway, as we mentioned, the meaning of R square, that just gives us a better idea of how well that line is actually fitting the data there. So again, the higher the R square value is, the closer it means that that one particular independent variable is really describing the relationship with a dependent one, right? And again, what's the highest R square can go? 1, right? So one relationship means that all the data points fit directly on that line. There's no variability there, right? If it's less than 1, that means there's going to be some amount of variability that's not explained just by that particular model. Yes, sir.
So with more factors, the R squared increases?
Potentially, but you'll see that you'll have different R squared values based on each independent variable you're going to look at. But what we'll see is that you can sometimes account for the other independent variables here, right? So for instance, say I'm looking at creatinine clearance and I'm looking at age and race. When I do that, when I'm doing a multiple regression, you're going to find that I'll have an R squared value that takes into account the race of the patient and only looks at the factor of age. So I take out that part of it. I take out that confounding that could skew the data, and we're looking at the factor of age and creatinine clearance. And then I can take into account whole age, take out the effects of that, and just look at the race of the patient and see how that affects creatinine clearance, right? So again, you can account for these different variables, and you're going to see that, okay, well, maybe age is accounting for, say, 30%, and then the race is accounting for, say, 15%, and then you can still find out other variables as well. And again, these are just random numbers, but you can see how that'll have an effect there. And I'll show you an example of that in just a few minutes here. So as I mentioned, looking at comparing, say, the model that you have that you've developed for your data, oftentimes when you're comparing that, the first thing you're going to do is look at the null hypothesis. And again, null hypothesis is just a straight line. And again, you don't have to figure out necessarily how they come in and determine the actual math here. Oftentimes we're using things like the sum of squares and do some calculus and whatnot, which is outside of our purpose here. But the big thing we're doing is we're looking at the difference between the models. We're looking at that straight line as our null hypothesis, comparing it to our best fit line, and looking at that difference there. And that's where that R squared value can come up and help us out with this. and say how much of that variability is being accounted for with our best fit line. Okay. Okay, so then that's basically the simple linear regression, getting into more various types of linear regressions are fine, but again, they don't tell us all of the data. And very frequently you find that a lot of studies are going to be looking at linear regressions or multiple linear regressions because they factor in more of those variables. Because it'd be nice if we could just have, you know, one-to-one factors here and all that variability is explained, but people are complicated, as I mentioned. So it's good to factor in lots of different variables here. And that's what things like multivariable regressions are going to help us with. Okay. Again, in lab experiments, I can control the variables. So I'm going to be setting what the independent are going to be, and then look at my outcome, my dependent variable, and see how that changes there. Okay. So as I mentioned, when you're looking at these in some kinds of experiments, and again, most of the times these are observational experiments. So when I say observational, what does that mean, do you think? Basically, I'm just like observing what's happening, right? I'm not actually making any kind of interventions as you go along, right? So again, if I were just to take, for instance, and actually it's kind of interesting, I mentioned in one class to some students, I said, oh, it would be really interesting to see what cortisol levels did throughout the PA career, like to see if, you know, based on the summer you come in, if it's like pretty low, but then around like, you know, the fall semester starts to increase and the winter semester gets even higher. Like some of my students actually did that in a different class. And so actually the study is ongoing right now, but they're looking at it. And it was based on observation, right? Because again, they're not doing anything. They're not trying to change like, hey, we're going to give you a bunch of really hard tests in 1 week and just to see how that changes the cortisol levels. That'd be more of an interventional sort of study. This is something we're just observing and see how changes occur over time. And again, they can take into account different variables as we'll see here. But again, this is a very widely used thing when you're just observing a big set of patients and you're taking into account all these different independent variables and looking to see how it affects that dependent variable. Again, I'll show you a good example of this in a moment here. But again, this is where we can assess the impact of, say, one variable while controlling for others. So if I'm looking at creatinine clearance, I can take into account, you know, I can control for things like the effects of age. I can control things like the effects of gender and just look at, say, the weight and how that affects creatinine clearance, you know. And then I can change it around and say, okay, I'm going to control for weight. I'm going to control for gender. Let's look at, you know, age and see how that affects creatinine clearance. And they can help us to make these really good predictions, and now I can apply it out to the greater population, right? Okay. So again, looking at some of the lingo here, when you say the different types that are going to happen here, anytime you're including multiple independent variables, this is where you're going to have what we call a multiple regression. Again, multiple independent variables are going to be explaining one particular outcome or one particular dependent variable. Okay. Again, the variables we mentioned here, dependence always going to be on the y, independence always going to be on the x-axis. And then when you say multivariate, this is probably not, multivariable is more the thing we're really kind of referring to here. Multivariate, just kind of get into the semantics of it, is where you're looking at different outcomes. We're mainly just going to be focusing on different input variables essentially, right? So again, we're looking at multivariable analysis. However, you may see multivariate out there. That's when you're looking at multiple outcomes. Okay, so this is kind of putting the rubber to the road, so to speak, and getting into an actual, you know, kind of more sort of real world example here. So again, looking at the multiple linear regression, this is going to be an example of that. We're going to see like what different independent variables can help us to explain the variability that we get from the value, our dependent value y. And so this is an example here, and the question they were asking was, does lead, and we know what the atomic symbol for lead is? PB, yep. So you ever see someone eating a PB&J, make sure it's not a lead and jelly sandwich. That would be bad. They said, does lead account for decreased kidney function with age? Okay, so that was their initial question. Now, in this case, what would the null hypothesis be? It doesn't. Yeah, lead has no effect on kidney function with age. Okay, so they want to find out, okay, can we reject this null hypothesis and find out if lead has a factor here? Now, we mentioned creatinine clearance, again, which is going to be our surrogate for kidney function, can be affected by several things, like what? Age, race, gender, weight, you know, use of medications, maybe nephrotoxic medications, hypertension, diabetes. There's a whole litany of things that could be affecting our kidney function, right? And so again, the more you take into account here, the more powerful of a model you can make to try to explain some of these differences you'll see here, right? So again, what they were trying to do in this particular study is that they had the hypothesis that lead decreases kidney function. And then we also know that kidney function decreases with age, right? I'm pretty sure everyone can say that, yeah, that's probably true. And again, if you didn't know, lead does have a negative effect on kidney function. But let's say we're trying to figure that out and see what kind of relationships we can find here, right? And again, what's a normal lead level for people? Actually, zero. Lead has no biologic function in the body, right? If anything, it's just a poison. But people tend to accumulate lead over the course of their life because lead actually looks a lot like calcium and has a very long half-life because it gets incorporated into bones and things like that, which is why kids are so potentially really affected by lead due to their developing bones and CNS and all that. But basically, they wanted to say whether accumulation of lead over time could cause a decrease in kidney function seen with age. So they're looking at not only age causing a decrease in kidney function, but could also that microaccumulation of lead over the period of their life also have an effect as well. That's what they're trying to answer here. And again, the null hypothesis would be there's no difference. So what they did, and again, the data we're just looking at here is just going to be the male patients. We'll look at a female study in just a few minutes. Let's say we have 965 men. So is that a pretty good sample size? It's pretty good, right? It'd be nice if you could look at thousands, millions of patients, but again, that gets expensive, that gets difficult. 965 patients, that's a pretty good study for most people, right? So let's look at the data set for men. They're measuring serum lead concentrations. They measured creatinine clearance, and again, what they found was subjects with more lead tended to have a lower creatinine clearance. But they wanted to figure out, well, okay, was that just due to the factor of age, or was it actually due to the fact of the lead that was present as well? And so we can try to tease that out by trying to control for these different independent variables here. Okay, so I'll show you some examples of that in a second. And again, the differences in age confounds that data because it can skew that data, right? We don't know if is it the lead or is it the age factor here, or is it a combination of the both? Well, let's try to figure that out by controlling for the confounders, okay? If I was trying to control for other confounders like use of diuretics, if I was trying to control for a confounder of in this case gender is not a factor because I'm only looking at male patients, but if I was looking at male and female, I can control for that as well. Again, those are confounders I can control for. All right. So to adjust for the confounder, they were going to use multiple regression, and they were going to adjust for age and also several other factors as well. And just note that here on our lead concentration, they're using the log of the lead concentration. It's still an independent variable, but just because they're looking at kind of a wide range of concentrations, using the log tend to be a little bit easier for them there. And again, our y variable, or the dependent variable, is creatinine clearance, right? And why is it the dependent variable? Because I said so. It's because that's the outcome we're looking for, right? We want to see what effect that the lead with age has on the creatinine clearance. That has to be my outcome variable. That's what I'm actually interested in looking at the change of, okay? And again, I'm looking for a model that best predicts how those changes in my independent variables causes changes in my dependent variable, right? So if I change the lead concentration, how does that affect the creatinine clearance, okay? So anyways, looking at this, some of the different factors they looked at included things like the log of the serum lead concentration, which I mentioned before, the age of the patient. We can look at the body mass of the patient. We can look at the log of the GGT they're measuring there, use of diuretics. And again, that was all going to be factoring in to see, okay, what was their concentration, their creatinine clearance? What was that outcome there? Now, again, does this include every single factor that could affect the creatinine clearance of the patient? No, there's other things that could certainly affect it as well, but they take kind of the most likely things I think that could have an effect on their patients, right? And again, it gets more costly the more of this that you do. Again, that's more measurements you're having to draw from the patient. So for instance, if you're trying to control for more things like, okay, well, what was their potassium levels? Maybe that has an effect. Or maybe you're looking at other things. It tends to get more expensive, gets more involved. And so typically you're going to say, before you start a study, say, these are the things I'm going to look at. These are the independent variables I'm going to control for. Now, again, is it good science to kind of go back, if you don't find anything, go back and say, well, let's maybe look at these other variables instead? No, you always want to do things a priori. You always want to go into a study thinking this is what I'm going to do beforehand, because otherwise you get into the problems of having multiple comparisons. You kind of run the experiment until something kind of works. That's not good science, right? Because again, we know that things are going to happen just with chance alone. If you run an experiment enough times over and over again, even a blind squirrel finds a nut. You can get results that are erroneous in those cases, right? So again, when you find a false positive, what do you call that? Type 1 or 2 error? It's a type 1 error, right? So again, if I kept running experiments until I found something, that's a type 1 kind of error there. We don't want that, right? I'd rather not find a false positive because that would lead me to an erroneous conclusion. Anyway, looking at this, again, you can kind of see the units they're looking for here, age and years, obviously. Now notice all these different independent variables, do they have to be in the same units? They don't have to, right? So again, you can have pretty variable there. You could have things like, diet. Are they eat protein or are they vegetarian? You can have all kinds of different things. They could be continuous. They could be categorical sort of data. They could be, ordinal. It can be anything here, right? Usually you're going to find that most of the time it's going to be more continuous data, but but the units really don't matter in this point here. But if you look at this with diuretics, see how they converted diuretics? So it's a yes/no, kind of a binomial sort of indication there. That's, 0 was never took diuretics, 1 took diuretics, right? So that's how you can convert some of that data into more sort of continuous like data there, right? What do you call that when you have data that's like yes/no, man, woman, red, blue? It's nominal variables, right? Those are nominal variables. If I said something like, strongly disagree, agree, strongly agree, what do you call that? That's ordinal, right? Because again, there's an inherent relationship between them. There's an order to it, but I can't necessarily quantify the difference between one to another, right? And again, what do I call if I said, looking at temperature? It's going to be continuous data, right? Because again, it can go all the way from 0, could be negative, could go continuously up, right? Again, there's a set difference between, say, 1 degree centigrade to 2 degrees centigrade as between 100 to 101. Good concept to know, right? So looking at the goals here, right? So our multiple regression is trying to fit a model is going to closely fit the data that we pull, right? So looking at the creatinine clearance and looking at all these other variables here to try to make the model come as close to fitting that data as possible, okay? Again, it'll give us a best fit value for each parameter, and it'll also give us a confidence interval as well, right? And it's going to tell us whether or not there's a significant relationship between these two, or if the confidence intervals we're going to find that could also tell us maybe there's no relationship whatsoever. So maybe we can find that some of these tend to not be significant at all, and there's no actual correlation between the two, that one does not accurately really describe the outcome, which is our creatinine clearance here, okay? And you'll see the 1 p-value gets reported for each independent variable. We'll look at that in a second. But again, less than 0.05 is typically considered to be statistically significant, okay? And again, the null hypothesis would be that the parameter provides no information and that value would equal 0. So what you're going to find here when you look at the confidence intervals is that if it crosses 0, you're going to find that that's actually going to be an indication that's a non-significant finding there, okay? So looking at this, again, the multiple linear regression doesn't really distinguish about the different x values. I have to take all those values and then I have to kind of apply, the interpretation to it, right? So again, this is where your mind comes in, the critical thinking, saying, okay, well, how do these results actually stack up? We'll look at some examples here and we'll actually look at the table to see how these stack up in a moment. Okay, so what they found is that when they had the best fit line for the lead concentration, and again, when you're looking at one of these independent variables, when you do a multiple linear regression, you're taking into account and you're controlling for all the other variables, right? So I'm accounting for the body mass of the patient, I'm accounting for the age of the patient, I'm accounting for the serum GGT, for the diuretic use, right? And I'm just looking at the effect of lead and the effect of creatinine clearance, right? Because this is the log of the lead concentration here. So basically what you're able to find is that based on that, the best fit line, the slope was negative 9.5. So based on that negative number, what does that mean? As lead concentration goes up, creatinine clearance goes down, right? Which makes sense. We say, okay, well, lead we know is a poison, and we know it's going to be toxic to the kidney cells. That makes sense, right, physiologically. So that means every unit of lead changes, you should see a decrease in creatinine clearance about 9.5 mLs per minute. And looking at the confidence interval, it was negative 13.9 to negative 5.1. So again, there's some variability there, but it should be somewhere within that range. We're 95% confident that it's actually in that range if we were to apply it out to a greater population of male patients. Because again, we're only looking at male patients in this particular case. Now, if this had, say, went from, say, negative 13.9 to, say, 1.2, and it crosses that 0 mark, you would say that that's non-significant. You'd say, and again, a lot of times you're going to find, and hopefully by the end of this class, you don't even have to look at p-values. You don't even have to look at a p-value to know if something is significant or not based off of if it's crossing a certain threshold. In this case here, if it went past 0, you would say that it was a non-significant finding here, right? Because there's not enough evidence to say that there's a strong enough correlation to say like, well, I don't know if it really increases it or decreases it. We just can't say based off the data. But here we have a confidence interval that does not include 0, so we can say, yes, this is statistically significant. And basically what that means is that because we're looking at the log of the lead concentration, a 10-fold increase in lead concentrations cause about a 10% decrease in creatinine clearance. Again, looking at this on the graph, you look at the change in lead concentration, you can see the kind of the best fit line, and this is your confidence interval between either side there, okay? Again, if this was something that crossed 0, so if again went positive, that would show that this line, it would not be statistically significant, okay? So we cannot clearly say that lead concentration, when accounting for all these other variables, affected the creatinine clearance significantly, right? Okay. As I mentioned, does not include 0. It's a negative number. So again, you already know that the p-value is going to be less than 0.05. Again, in this case, the authors actually didn't have to quantify. You just know based off of the confidence intervals that yes, it is less than 0.05. Okay. other examples of that, so get a better feel for that. Now, when you're looking at how well does that data actually fit that model there, the multiple regression report had an R-squared value of 0.27. So what does that mean? So that means only 27% of the variability in the creatinine clearance was explained by the lead concentration. So while lead is important, it's not the whole story, right? So again, you're going to find that when you're looking at the other independent variables, you'll find those also have an R-squared value associated with them. So what do you think age would be as far as an R-squared value compared to lead? Think it'd be more likely to be causing, be more likely to cause a correlation with that variability? Probably, right? If I have a 90-year-old patient, they're probably going to have a lot less kidney function than someone who says is 20. So looking at that, you could probably reasonably assume that something like age would have a bigger R-squared value. Again, it's going to be explaining more of that variability here. Lead, while it explains probably about a quarter of that variability, there's still about 73% that could just be random. And again, that means we've already taken into account all those other variables we're looking at. This is just looking at lead and creatinine clearance there. Okay. Again, if you were to say extrapolate out this data, looking at this, just looking on between the creatinine clearance and the lead concentration, you'd find there's just so much scatter there that again, it would not be really the best fit line. It doesn't give you the whole story there, so it's hard to make a lot of conclusions off of that. We do know that there's a relationship, but again, we know there's a lot of variability that's also going to be playing a role here. Not just lead that's going to be the biggest player. Okay. Okay. So any questions from the first half that we talked about? And again, I cannot stress this enough. This test does not have to be hard, but the later you wait to watch all this stuff and review it, the later you're going to find that, oh no, I actually don't understand this. I need to go talk to Dr. Wood. And then it might be like the night before the test, and that's too late, right? So you want to identify these things. If you're like, I just don't get this, like that's okay, but come to me, let's talk about it beforehand or email me or something. But the day before the test, unlikely to be the time to really solidify your knowledge of the stuff, okay? So sooner rather than later. Anyway, so as I mentioned, we're talking about correlation. We're talking about these linear regressions. Now, again, does this imply causation? Can we say specifically that lead causes decreased kidney function? No, we say there's a relationship, right? We say that, hey, some of this variability can be explained when you increase the lead concentrations. You see a decrease in creatinine clearance. However, it does not say specifically that lead causes that. Now, how could we figure that out, though? I could do a study, right? And again, oftentimes you'll do things like prospective studies. Say prospective, what does that mean? I start a study today and I look at data going forward, right? So say, for instance, I were to give, say I split you guys up into thirds and I give lead, I give you a little bit of lead, and then I give you guys all the lead. And I look at your creatinine clearance a year from now. Does that sound ethical? Not really, right? So because of that, you can't really do studies like that. So sometimes we're just have things like observational studies, but you need to do things like prospective studies to find that out. Does this count as my evaluation if you just sit and listen?
Yes.
No?
Yes.
No? She's like, no, I want to get out of here. I don't want to hear this stuff. Anyway.
It's exciting.
Yes. We instill confidence. Anyway. Right. So, and again, you need to do a different type of study to figure out cause and effect. And that's where things like prospective studies come into play here. Okay, so looking at logistic regression, this is actually where you can start to include looking at two possible outcomes, right? So now we're looking at two different outcomes here. Here's an example of one where we're looking at the prediction, look at the prevalence of obesity, and this happened to be a study that was done in Iranian women. And again, the outcome here was obesity, right? So it was kind of a binary thing. They're either considered to be obese or not obese, based probably off of BMI is what they're using here. And again, what they did was they created a model to try to look at the different variables that go into determining what's that prevalence of obesity. What are the things that are likely to have led to that woman being potentially obese or not? Okay, and they looked at different demographics. So here's what they did is they looked at three independent variables. They looked at things like age, number of years of education. And again, those are continuous variables, right? So those are things like age, the difference between year 1 to year 2 is the same difference between 71 to 72 years of age, right? Again, that's going to be continuous data there. Same thing with years of education. Now looking at smoking status, marital status, what do you consider that? What type of variable is that? It's more of a nominal variable, right? Because again, it's a yes, no sort of thing. or it could have more categories than that, but it's something, there's no inherent relationship necessarily, right? You may think there is, but there really isn't. So for instance, I can say yes, you're a smoker, not a smoker, marital status, married, not married, whatever happens to be. Place of residence is where they looked at like urban versus non-urban place of residence. And then here they were looking at economic index, and they had 4 different categories, and they actually converted these into binary variables. So they said, are you a high socioeconomic status, yes or no? Or are you low economic status, yes or no? Alternatively, you could have done that as like an ordinal variable. We could have said low, medium, and high socioeconomic status. You could have done that sort of an ordinal sort of variable. Again, where there's no inherent relationship. There's a relationship between one being more than the other, but there's no inherent actual value between those two. So anyway, so I had 14,000 women they had in this study, which again, is that a pretty good sample size? It's a great sample size, right? So you can take a lot of data from that and say that, yes, this is probably pretty representative of the whole population here. But they use logarithms. This helps us convert odds ratios. Now, if anyone's watched the videos, we've covered odds ratios. Again, this is usually something we're doing when we're looking at retrospective data, right? So we're taking data and looking backwards in time. We use a lot of odds ratios there. Odds ratios are just looking at the odds of a person, in this case being obese, versus the odds of them not being obese. And then we're doing ratios between these different variables here, as we'll see. So we'll show you some examples of the outcomes here in a minute. So anyway, looking at this, the example we're going to see has 8 independent variables here. So the model ends up showing up with 8 odds ratios, right? And so these odds ratios are going to tell us, basically each of these variables, what are the odds that if a woman has this variable that she's going to be obese, okay? And so again, the higher the odds ratio, the more likely that woman is to be obese. If that value was less than, say, 0, what would you consider that? I'm sorry, if it's less than 1, what would you consider that to be? You'd actually have a protective effect. You'd actually find that it would actually make the odds of you being obese or those women being obese lesser than if they did not have that variable. So I'll show you, it'll make more sense in a second here. But again, each of the odds ratios is trying to say that if I were to increase that value by 1, what are the chances it's going to actually lead to that bigger odds that they're actually going to be obese? This. Looking at the odds ratio, if it's near 1, because again, we're looking at ratios, you're comparing thing 1 divided by thing 2, right? So again, you're looking at odds ratio. Instead of looking at 0 as our area of looking for significance, now it's going to be 1. So if something crosses 1, that means it's going to be non-significant. If it doesn't cross 1, then it means it's going to be statistically significant, right? So you don't have to look at a p-value to tell you that. I'll show you what that looks like in a second. If it's much higher than 1, that means you have a much higher likelihood. The odds are going to be higher that you're actually going to be obese. And then if it was less than 1, and again, you couldn't have 0 or less than 0, but if again it's between 0 and 1, that means it's going to have more of a protective effect. Your odds of being obese are lesser than, and if you didn't have that variable, okay? And so looking at you look to see, okay, the different odds ratios we have here. So for instance, we have urban, right? So again, if they are living in an urban environment, and again, the whoever's running the experiment determine what is considered to be urban or not, right? And so you see an odds ratios of 2.13. So the question is, what does that mean? That means that if you were a woman living in an urban setting here, based off of their definitions, the odds of you being obese were 2.13 times that of someone who lived in a non-urban setting. So it means if you live in the city, more likely to be obese. Okay, and then you see the odds ratios here. Now notice 1.9 to 2.3. Now does that cross 1? No, it stays above 1. So because of that, we know that this would be a statistically significant observation. We'd say that, yeah, it looks like that the odds of being obese are higher for these women when they live in an urban setting. Okay. Now, looking at something like age here, see age 1.02. So what do you think age has an effect on? What does that mean for the effect on the odds of someone being obese or not? Very close to 1. So again, when you're doing a ratio, one thing divided by the other, if they're identical, that ratio is 1, right? So that means the closer it is to 1, then it probably doesn't make a whole hill being a differences. The odds are not that much greater there, right? So again, you have maybe a 2% higher odds of being obese in this case, which isn't really that much. Now, it's still statistically significant because it doesn't cross 1. But again, you notice here we talk about things like clinically significant versus statistically significant. Just because something is statistically significant, does that mean it's clinically significant? No, right? You can have a statistically significant difference between something, but if it's such a small, minute change in value that it doesn't really matter to me as a clinician, I don't really care, right? So again, you can find things that are significant all day long. It doesn't mean it actually means that will be differences to your actual patients here. So again, age probably doesn't have a big role to play here, even though it is significant. Education. This looks like, again, is pretty close to 1, even though it looks like education, the more education you had, probably led you to be have less odds of being obese. However, the change isn't really that big here. Still significant because, again, the more sample size you have, the more likelihood you're going to find those significant results that they're actually there, right? Because again, the more people we have, the more power that you have to find those differences, right? Now, again, if there was an actual difference here, so say for instance, I was only looking at say 100 women, and this value was 0.98, but it ended up crossing over into say 1.02. You would say, well, that's not significant. But anytime you have something you say, well, this is non-significant, the question is, well, did I have enough people actually show that difference? And so by increasing your sample size, having more power, you're more likely to see those actual differences there. Now, when you have an experiment and you don't see a difference, but it truly is there, what do you call that? What type of error is that? It's a false negative. You call that a type 2 error, right? That usually means you didn't have enough power to find the difference if one actually exists there, okay? And again, oftentimes you'd rather make a type 2 error than a type 1 error. Type 1 we mentioned is a false positive, but again, that usually goes back to power. More sample size, more power you have to find differences. Okay, so going from that, looking at smoking. So what do you think about smoking and the odds of being obese here? Seems to be protective, which kind of makes sense, right? Smokers tend to lose weight, right? Because again, you find that nicotine acts as a stimulant. This would make sense, right? So people that smoke, these women that smoked in the study, tend to be less likely to be obese based on the odds here, right? So 0.65. That means they had 35% roughly decrease in the odds of them actually having being obese compared to women who are non-smokers here. Now again, looking at this, the confidence interval, see it does not cross 1, you still consider this to be significant, okay? But again, this is more clinically relevant than something like the education, which is 0.98, right? It's not a big difference here versus say, 35% change there. It's a lot bigger, okay? Looking at things like married, anyone married here, you know that you tend to not care as much about what you eat, so I can definitely attest to that. Tend to gain a little bit of weight afterwards. That makes sense, right? But again, this is statistically significant. All these were things that tended to make you more likely to be obese than if you were to not fit into one of these categories here, okay? Does that make sense so far? So again, odds ratios are basically what we're using because again, we're looking back at the data. We're looking retrospectively because you have all these women here. You're basically doing a survey on them and asking them questions like, "Hey, do you smoke? Do you live in an urban setting? All these things." And then you're looking backwards. So that's why we're using odds ratios here, right? When you're looking forwards, we're going to see this is when we're doing things like risk reductions and risk ratios. So again, if you go back and look at the lectures online, you'll see those. That's what we're going to talk about there. Okay. Okay. So again, looking at the results, logistic regression is going to compute those odds ratios for each of those independent variables with that confidence interval. As I mentioned with the, say for instance, the women living in the city, 2.13 odds. So again, much higher odds than them being obese than if they lived in a non-city sort of setting there. Again, twice the odds of being obese as someone who does not. Again, that's when we're controlling for all the other independent variables. We're controlling for education, we're controlling for smoking, we're just looking at the effect that where they live versus whether they're obese or not, right? Looking at that, so that's very helpful there to looking at that. Again, this is a significant finding because it does not include 1. And again, the p-value has to be less than 0.05. We already know because it does not include 1, we can just safely assume that the p-value is less than 0.05. Okay, and again, a lot of times you don't need to even look at the p-value to know whether something is significant or not. This is another example of that. Okay. So going into a couple of questions here. So does the x and y values have to have the same units to perform a linear regression? No, we saw that does not have to be the case there. You can compare vastly different units between one another, and that is totally fine there, okay? So again, looking at the, say for instance, looking at obese, yes or no, versus, smoking, yes or no. Like, so those don't really even have units. They're just kind of binary variables there. But if you look at like, insulin sensitivity versus the percentage of fatty acids, different units there, and that's totally fine to compare those two when you're doing linear regressions. Linear regressions, can they work when all the x values are the same? Or how about when all the y values are the same? So again, if you're looking at this and you're looking at a linear regression, you see all the x values, right? All the y values are the same in this case, or if there were all the x values are the same. You can't really tell any variability there because you need some variability in the x or the y in order to find some sort of relationship there. So that does not actually work in those sort of cases, okay? And finally, will the linear regression be the same if you exchange x for y? That would not be the case, right? So again, you need to make sure you're determining what your independent and your dependent variable are, because again, when you're doing like a regression, you're trying to determine what can I predict from y based on my changes in x, okay? All right. So again, we already talked about those. Review that if you need to, but you always have to decide which variable is the outcome dependent and which ones are going to be the predictors, the independent variables, when you're at the time of data collection. it's a good idea to do that, right? You can go back and torture your data and try to find something after the fact. However, that's not good science, right? Not to say that doesn't happen. Certainly does, but again, if you were the perfect scientist going forward, you would say, hey, I want to make sure I have all my variables already figured out, which ones are independent, which ones are dependent, and going forward, that way you avoid using those multiple comparisons issues, right? Again, just comparing things until you find something that is significant there. Okay. Does it make sense to compare the value of one best fit parameter with another? You can in some cases, right? So being able to kind of look at the variability of those R squared values can be useful in trying to compare one versus another. It can be sometimes useful there. And all the independent variables have to be expressed in the same units. They do not, right? So we kind of mentioned those units can be different than one another. Again, you're kind of looking at the best fit line in those cases. That's what you're really looking for. You're looking for those R squared values. You're looking for those confidence intervals there. Okay. All right, so any questions on linear regressions?